How do you feel about revisiting your high school chemistry education? Well, that step might be necessary as an update has just occurred to the periodic table. Scientists have discovered brand new elements, but what shocks them most is how the discovery changes everything we know about the periodic table. What are these new elements and why are they causing so much excitement? Join us as we dive into how scientists just discovered elements beyond the periodic table that change everything. One of the tables many people may not know about but affects their lives fundamentally is the periodic table. A periodic table is a diagram that depicts all known elements and their properties. While it might appear unassuming, it is an essential instrument for chemistry and science in general. But how did it happen, and most especially, what's the deal with the gaps on the table? The first attempts to organize the elements were based on their atomic weights and their chemical behavior. For example, John Newlands discovered that the properties of every eighth element were similar and named this the law of octaves. Julius Meyer classified elements based on their atomic weight and the number of atoms they typically combined with. These methods, however, suffered from considerable limits and inconsistencies. In 1869, a Russian chemist named Dmitry Mendeleev developed one of the first workable periodic tables. He grouped the elements according to their atomic weight and valence, that is, the number of electrons they can lose or gain. He also discovered that elements with similar features arrange themselves into vertical columns, which he dubbed groups. He designated horizontal spaces as periods for things that did not fit into his framework. Mendeleev was certain that his periodic table accurately represented the natural order of the elements. He projected that undiscovered elements would fill the gaps in his table and correspond to the features of their groupings. He even gave them tentative names like Eka aluminium, Eka boron, and Eka silicon. He also challenged certain previous statistics and corrected several atomic weights based on his table. The discovery of additional elements that suit Mendeleev's gaps quickly validated his predictions. In 1875, for example, a French chemist discovered gallium, which had nearly identical characteristics to Eka aluminium 3. Clemens Winkler, a German scientist, found germanium in 1886, which matched Eka silicon. Lars Fredrik Nilsson, a Swedish scientist, discovered scandium, which corresponded to Eka boron in 1879. Mendeleev's periodic table was validated by these findings, which made him renowned. Nerdy fame, but fame remains fame. Mendeleev's periodic table, however, was not perfect either. It contained some oddities and irregularities that could not be explained only by atomic weight. Iodine, for example, has a higher atomic weight than tellurium but was placed ahead of it in the table due to its chemical similarities to chlorine and bromine. Furthermore, other elements such as cobalt and nickel have extremely similar atomic weights but very different characteristics. But the early 20th century saw the discovery of the structure of the atom and its subatomic particles, protons, neutrons, and electrons, which solved these difficulties. They realized that for defining an element, the atomic number, that is, the number of protons in the nucleus, was more basic than the atomic weight, which is equal to the sum of protons and neutrons. They also discovered that electrons occupied various energy levels surrounding the nucleus, which influenced their chemical behavior. In 1913, Henry Moseley, a British physicist, utilized X-ray spectroscopy to determine the atomic numbers of all known elements. He discovered a definite relationship between an element's atomic number and the frequency of X-rays emitted. He also changed the periodic table by raising the atomic number rather than the atomic weight. This resolved most of Mendeleev's table's anomalies and irregularities and established a new periodic law. Elements with similar characteristics have similar electron configurations. Moseley's work also revealed that the periodic table still had some gaps for elements with higher atomic numbers than uranium-92, which was the heaviest known element at the time. He anticipated that there would be at least 14 more elements discovered after uranium. However, he perished in World War I before completing his studies. The discovery of these new elements, though, necessitated the development of new procedures and technologies capable of producing them artificially. Because they were highly unstable and radioactive, these elements were not found in nature. They degraded swiftly into lighter elements. Particle accelerators were employed by scientists to blast atoms with high-energy particles and fuse them together to generate new elements with higher masses. Technetium-43, the first synthetic element, was synthesized in 1937 to fill the void left by element 43. It was followed in 1940 by astatine-85, in 1945 by promethium-61, and in 1939 by francium-87. These elements were later discovered in trace concentrations in nature, although they are still considered synthetic due to their ease of production. The next task was to synthesize atoms with atomic numbers greater than uranium, which possess the highest of any naturally occurring element. This necessitated a method other than neutron bombardment, which could not overcome the tremendous electrostatic resistance between two heavy nuclei. Particle accelerators were used by scientists to smash lighter nuclei together at high speeds and fuse them into heavier ones. This process is known as nuclear fusion, and it produces a large amount of energy. In 1940, nuclear fusion produced the first element, neptunium-93, followed by plutonium-94 in the same year. These components were part of the Manhattan Project, which was responsible for developing the first atomic bombs during World War II. They also played a vital role in nuclear reactors and weaponry. Following the war, the synthesis of heavier elements proceeded with the collaboration and competitiveness of various laboratories throughout the world. The Joint Institute for Nuclear Research, JINR, in Dubna, Russia, and the Lawrence Berkeley National Laboratory, LBNL, in Berkeley, California, were the most visible. To generate new elements, they used several types of particle accelerators and diverse combinations of target and projectile nuclei. They created 24 new elements between 1944 and 2010. These are all synthetic and super heavy elements, which means they have very big nuclei that are unstable and decay quickly. Their half-lives are extremely brief, ranging from microseconds to minutes. They also have very low yields, which means they can only create a few atoms at a time. This synthesis is not simply a scientific accomplishment, but also a cultural and political one. These elements' names reflect the history and geography of their discovery. For example, Einsteinium-99, Fermium-100, Mendelevium-101. Remember Mendeleev of the periodic table fame. Nobelium-102, Rutherfordium-104, Seaborgium-106, Bohrium-107, Meitnerium-109, Röntgenium-111, and Copernicium-112 are all named after famous scientists who contributed to nuclear physics or chemistry. Fancy having an element named after you. And some elements, such as Berkelium-97, Californium-98, Dubnium-105, Darmstadtium-110, and Livermorium-116, are named after localities where they were discovered or where the discoverers came from. Some elements, such as Lawrencium-103, Hassium-108, Fluorevium-114, are named after nuclear physics or chemistry concepts. Now, the combination of these components raises several issues and questions for science and society. The existence and properties of these components must be confirmed, which necessitates sophisticated detection technologies and worldwide collaboration. Another issue is producing longer-lived isotopes of these elements, which would allow for more extensive examinations of their structure and behavior. A third challenge is to investigate the possibility of producing heavier elements, which could reveal novel phenomena and insights into the nature of matter. Nihonium is one of the periodic table's newest and most intriguing elements. It has the atomic number 113 and the symbol NH. It is a synthetic element that does not exist naturally on Earth and must be generated artificially by rapidly colliding nuclei. It is also exceedingly radioactive and unstable, which means it decays swiftly into lighter elements. The discovery of nihonium was a lengthy and complex procedure involving numerous international teams of scientists. A Russian-American partnership, the Joint Institute for Nuclear Research in Dubna, Russia, made the first claim of producing nihonium in 2003. They used calcium-48 ions to attack americium-243 atoms and found a single atom of nihonium-287, which degraded into moscovium-2831. Other laboratories, however, were unable to validate this conclusion. A team of Japanese scientists at Riken in Wak, Japan, claimed to have created nihonium in 2004. They employed the same technique as the Dubna team, but with a different detector. 3 atoms of nihonium-278 were found, which decomposed into runtgenium-2742. Independent experiments in Germany and the United States later verified this result. The Riken team was officially recognized as the discoverers of nihonium by the International Union of Pure and Applied Physics, making it the first element ever discovered in Asia. Nihonium is derived from the Japanese word Nihon, which means Japan. Nihonium is a part of the periodic table's Group 13, Boron Group, and Period 7. It is expected to have chemical characteristics similar to thallium, with some changes due to relativistic effects. Nihonium, for example, may have a lower melting point but a greater boiling point than thallium. It can also be in the oxidation states -1, +1, +3, and +51. Outside of scientific research, nihonium has no recognized applications. It is extremely difficult to generate and study because just a few atoms may be created at a time, and they disintegrate rapidly. Nihonium-286 is the most stable isotope known, with a half-life of around 10 seconds. By producing longer-lived isotopes and studying their chemical reactions, scientists aim to understand more about the structure and behavior of nihonium and other super-heavy elements. Nihonium is an example of human creativity and curiosity pushing scientific boundaries. It is part of an effort to discover new elements and comprehend the nature of stuff. It also demonstrates how worldwide collaboration and rivalry can promote scientific understanding and discoveries. Another newly discovered element is moscovium. It is also the most mysterious element. It is represented by the symbol Mc and has the atomic number 115. It is a synthetic element that doesn't exist naturally on Earth and must be generated artificially by rapidly colliding nuclei. It is also exceedingly radioactive and unstable, which means it decays swiftly into lighter elements. Several teams of scientists from several nations collaborated to discover moscovium. The same Russian-American partnership at the Joint Institute for Nuclear Research made the first claim to have created moscovium when they used calcium-48 ions to bombard americium-243 atoms and found a single atom of moscovium-287, which degraded into flerovium-2831. But again, other laboratories were unable to validate this conclusion. However, the second claim of producing moscovium was made in 2009 at the same JINR laboratory by a team of Russian and American scientists. They followed the same procedure as the last team but with a different detector. They found 6 moscovium-288 atoms and 2 moscovium-289 atoms, which degraded into flerovium-284 and flerovium-285 respectively. Independent experiments in Germany later verified this result. Moscovium was formally recognized as the second element discovered in Russia by the International Union of Pure and Applied Chemistry and the International Union of Pure and Applied Physics eventually. And if it is not obvious already, moscovium is derived from Moscow Oblast, which is the region in which the JINR is located. Moscovium belongs to the periodic table's Group 15 or pnictogens and Period 7. It is expected to have chemical characteristics similar to bismuth, with some changes due to relativistic effects. Moscovium, for example, can exhibit oxidation states of +1 and +3 like bismuth, but also -1 unlike bismuth. It could potentially have a lower melting point and boiling point than bismuth. Moscovium has no known applications other than scientific research. It is extremely difficult to generate and study because just a few atoms may be created at a time and they disintegrate rapidly. Moscovium-290, the most stable known isotope of moscovium, has a half-life of roughly 0.65 seconds. By producing longer-lived isotopes and studying their chemical reactions, scientists aim to understand more about the structure and behavior of moscovium and other super-heavy elements. Moscovium exemplifies human ingenuity and curiosity. It is part of an effort to discover new elements and comprehend the nature of stuff. It also demonstrates how worldwide collaboration and rivalry can promote scientific understanding and discoveries. And there is yet another element joining the periodic table, and it is unique for being among the heaviest elements on Earth. Its name is tennessine element 117 on the periodic table with the symbol TS and a periodic atomic weight of 294. In 2010, a Russian-American collaboration announced the discovery of element 117. The same team confirmed their findings in 2012. A German-American team replicated the experiment successfully later. TS-297 atoms were created by blasting a berkelium-249 target with calcium-48, which then decayed into TS-294 and neutrons. The element was formally introduced into the periodic table in 2016. An acknowledgement of the contributions made by Oak Ridge National Laboratory in Tennessee, the Russian-American team recommended the new name tennessine for element 117. Because the element's discovery involves 2 countries and multiple research facilities, it was anticipated that naming would be difficult. However, some new elements have been validated, making it easier to agree on names. And the symbol is TS because TN is the acronym for the state of Tennessee. Based on its position on the periodic table, you might expect element 117 to be a halogen such as chlorine or bromine. Scientists predict that the relativistic effects of the element's valence electrons will prohibit tennessine from generating anions or reaching high oxidation states. Element 117 may resemble a metalloid or post-transition metal in several ways. While element 117 may not behave chemically like halogens, physical qualities such as melting and boiling point are expected to follow halogen trends. Unum septium of all the elements on the periodic table should be the most similar to astatine, which is directly above it on the table. Element 117, like astatine, will most likely be solid at ambient temperature. Tennessine has no recognized use outside of scientific research yet. It is extremely difficult to generate and study because just a few atoms may be created at a time, and they decay very quickly. Tennessine-294, the most stable isotope known, has a half-life of around 80 milliseconds. Scientists seek to learn more about the structure and behavior of tennessine and other superheavy elements by producing longer-lived isotopes and studying their chemical interactions. The 4th newest element is named after a larger-than-life Russian scientist, Yuri Oganessian, deservedly so. For 60 years, Oganessian has pushed the frontiers of the periodic table with his unique blend of creativity, scientific skill, and leadership. Before enrolling in the Moscow Engineering Physics Institute, Oganessian, who was born in Rostov-on-Don and of Armenian descent, aspired to be an architect. He chose to join the USSR's element hunters under Georgy Flerov there. He went on to develop the cold fusion approach, which produced elements 107 to 113, as well as hot fusion reactions with the neutron-rich 48Ca, which produced flerovium and other elements. Partnerships are an important component of modern science, and Oganessian establishes and cultivates them with warmth, understanding, and ardent scientific curiosity. The element that bears his name, Oganesson, is also one of a kind. It was created in 2002 by Oganessian's team at JINR and collaborators at the Lawrence Livermore National Laboratory, firing 48Ca at a 249Cf target. There is currently only one known isotope, 294OG, which was produced in such uncommon processes that it took 10 years to get 4 confirmed atoms. The 4th was a fortunate discovery. It resulted from an effort to synthesize element 117 by blasting a 249BK target with a 48Ca beam, but 28% of the target had decayed into 249Cf, generating element 118 instead. In 1999, the Lawrence Berkeley National Laboratory made an earlier claim for element 118 rather than Russia. 3 decay chains, the results of a krypton beam into a lead target, were published shortly after the death of Glenn Seaborg, who led or participated in the discovery of 10 elements, including plutonium. It appeared to be almost too good to be true, and it was. Other groups, including the Berkeley team, were unable to replicate these decay chains, prompting the Berkeley team to reanalyze the original data. When no proof of the chains could be located, the publication was retracted by all authors except the first author, Viktor Ninov, who was in charge of assessing the raw data. Ninov had been removed from Berkeley for scientific misconduct and had initiated a grievance procedure by the time the retraction emerged. The finding of the last element of the periodic table, as we know it now, is undeniable, but its structure and properties remain unknown. There has been no chemistry performed on this radioactive giant. 294OG has a half-life of less than a millisecond before succumbing to decay. However, theoretical models show that it may not follow the periodic trends, as a noble gas oganesson should have closed valence shells in a filled 7s27p6 structure. However, in 2017, a US-New Zealand partnership anticipated that this would not be the case. Instead, relativistic effects, that is, differences between expected and observed behavior caused by relativity, may result in shell structure degradation. These effects can be seen across the periodic table, becoming stronger as nuclei become larger. Oganesson appears to have arrived at the point where electrons form an equally distributed charge gas. Such alterations impact an element's properties. Oganesson may be a solid at room temperature and more reactive than its noble family due to the ease with which electrons in its p orbitals can be extracted. If the models are correct, it might be the end of periodicity as we know it, a watershed moment at the intersection of chemistry and physics. Oganesson, like its eccentric father, has the potential to be incredibly interesting. However, one big question is whether these aspects have any practical use or provide any benefits to humanity. Most of these elements have no recognized applications outside of scientific research at this time. Some of them, however, may have use in health, industry, or energy generation. Americium, for example, is employed in smoke detectors, curium in space probes, californium in neutron sources, einsteinium in nuclear synthesis studies, and copernicium as a super-heavy catalyst. Another debate is whether these elements are naturally occurring. Some may claim that these elements are unnatural and artificial because they do not occur naturally on Earth and are developed by human intervention. Others, however, may claim that these elements are natural and a part of nature because they are composed of the same fundamental particles as all other elements and obey the same physical laws. They may also claim that these elements are natural because they can be found in extreme situations like supernovae or neutron stars. Stars are the elements' factories. In their cores, they generate new elements by compressing components together in a process known as nuclear fusion. First, stars combine hydrogen atoms to form helium. Helium atoms then combine to form beryllium, and so on until fusion in the center of the star has produced every element up to iron. This process generates a large amount of energy, which keeps the star shining and keeps it from collapsing due to gravity. Fusion, however, cannot form elements heavier than iron since it would consume more energy than it would yield. Stars require a different source of energy to produce these heavier elements: gravity. When a big star runs out of fusion fuel, it loses the ability to resist its own gravity and collapses into a dense core. This causes a massive explosion known as a supernova, which shoots the star's outer layers into space. The shockwave from the supernova can compress and heat the residual core to the point that nuclei beyond iron can be fused. Elements such as gold, silver, platinum, and uranium are created in this manner. But what about the human-made elements? Can they arise in supernovae as well? Yes, but only for a brief period of time. Some human-made elements have slightly more stable isotopes than others. The half-lives of these isotopes range from microseconds to minutes. This means they can persist long enough in supernovae to be synthesized before decaying into lighter elements. Technetium-99, for example, has a half-life of roughly 6 hours, which is long enough for it to be created by neutron capture in supernovae. These isotopes, however, are extremely rare and difficult to detect because they are rapidly diluted by other elements in the interstellar medium. Artificial elements with no stable isotopes are much more elusive. The half-lives of these elements range from nanoseconds to milliseconds. This means they can only be formed in extremely hostile conditions where nuclei clash at high speeds and fuse into heavier ones. Such conditions could arise in neutron stars or black holes. These are the remains of enormous stars that collapsed due to their own gravity following explosions. They have extremely powerful gravitational fields that can attract and accelerate stuff. When two neutron stars or a neutron star and a black hole collide, a burst of gravitational waves and electromagnetic radiation is produced that may contain traces of these man-made components. These occurrences, though, are extremely rare and remote, and the artificial elements they make are extremely short-lived and feeble. As a result, observing and identifying them with present technology is extremely difficult. The only method to study these elements in depth is to artificially synthesize them on Earth using nuclear reactors or particle accelerators. Scientists can learn more about their features and behavior as well as test their assumptions about how stars form by doing so. These arguments, however, highlight a number of philosophical issues regarding the nature and definition of synthetic elements. What distinguishes an element as synthetic or natural? Is it the element's genesis, stability, quantity, or usefulness? How are these elements classified in relation to other elements and substances? In terms of their scientific, cultural, and ethical relevance, how do we value and respect these elements? These are difficult questions to answer, and different points of view may have different solutions. Some philosophers may use a synthesis approach in which they attempt to incorporate ideas, information, and arguments from several fields and domains in order to develop a more complete and coherent picture of synthetic elements. Others may use an analytic approach in which they attempt to clarify and assess the concepts, assumptions, and implications of various synthetic element views. Gaps in the periodic table are the result of the periodic table's history and current development as well as the synthesis of new elements. They depict science and technology's struggles and successes in generating and discovering new forms of matter. In comprehending and judging these new forms of matter, they also raise some interesting and crucial concerns for philosophy and society.